Hello everyone and welcome to session number 6 of this set of videos created to explore programming applications in reinforced concrete. In today's session, we will not be using Maple from MapleSoft. Instead, we will be using the programming language Python. I will come back to Maple in subsequent sessions to show you some really interesting applications. But for now, let us explore one of the most handsome programming alternatives. Python is a high-level, interpreted, and general-purpose programming language known for its simple, readable syntax that resembles English language. It is a beautiful language with a vast spectrum of available libraries that the user can make use of. You can download Python for free from python.org, and then you can download your favorite source code editor, which is the application where you will write, format, run, and test your developed code. I like to use Visual Studio Code, or in short VS Code by Microsoft, which you can download for free. Just type in Google Visual Studio Code and download the version compatible with your operating system. Google Anti-Gravity is another great choice for AI-assisted programming. To learn Python, there are plenty of free resources out there, including full courses on YouTube that you can watch and learn. In my personal opinion, people should learn Python no matter what are their disciplines in life, even just for fun. In this session and the upcoming sessions, I will show you applications created using Python, and I will demonstrate them from the simplest applications and then move up. We will start today with the flexural analysis of rectangular singly reinforced concrete beam cross-sections. But first, let us look at a very simple syntax example of coding using Python in VS Code. In this example, the first statement is a print statement. The second statement is a print statement as well. In the third and fourth statements, we are defining variables a and b, and we are giving them float format, and we are requesting the user to insert values for these variables a and b. Then we are printing the sum of a and b in the next statement. If we run the code by clicking on this play button here, then we can see the results displayed in the terminal here, where we are requested to insert a value for a. We've defined a as a float variable, so I'm going to insert 2.5, b 3.5, and the results are generated here. The sum of a and b is 6. Now if we look at this example, which is more related to our work, then we can use this print statement to state out that we are working with reinforced concrete cross sections. Then we can ask the user to insert a value for the width of the beam, b, the depth of the beam, h, and then we can print the gross cross-sectional area of the section, b times h. Let's do that by clicking on the play icon here. We are requested to insert a value for b. This is an integer now, so we're going to insert 250. Then h will be 500, and the result, the gross area of the cross section, is given as 125,000 millimeters square. If we are interested in the end product, where the user is into giving input and generating results without the need to see the code involved, then we can convert the developed Python code into a standalone application. Here the user needs to enter the required input parameters and click Run to see the output results. Let's look at an example of such standalone application. This here is the input file, which is a txt file, where the user inserts all the required input parameters. For example, the width of the beam, depth of the beam, yield stress of steel, compressive strength of concrete, and so on. Once these parameters are entered, the user can save the file and click here on this standalone application designed for the flexural analysis of singly reinforced rectangular concrete cross sections, and wait for the output to be generated. Now the output has been generated. You can see that it is generated from the time changed here, so we can click on output and check out the output file. Again, in this method, the output is formatted where you can see every result with its units right next to it, and each variable is assigned the required number of decimal points suitable for that variable. The output file shows the time and date. It shows the input parameters inserted by the user, and then shows all the calculated parameters in this section here. And eventually, if the beam checks out and it turns out to be tension controlled and satisfying all the ACI code requirements, then the final results are printed where we show the strength reduction factor phi and the final design strength of the cross section. Now let's say that the user inserted the following information into the input file. Let's say the user decided to use a 22 millimeter bar in the layer farthest from the neutral axis and 25 millimeter bars in the layer on top of it, 2 bars in the farthest layer, and 3 bars in the layer on top of it, which is not the most efficient use of steel. Let's save the information given and run the standalone application to check the output file. In the output file, we can see that Python has changed the diameter of bars. Python also changed the number of bars used in each layer, and indicated here that changes has been made to the input file. Changes has been made to the values inserted by the user. Here, it is explained that the diameter of bar in the layer farthest from the neutral axis should be larger than that in the second layer, and the number of bars in the layer farthest in tension should be larger than the number of bars in the layer on top of it for a more efficient use of steel. Now the output, the calculated parameters, they are all generated according to the corrected information. The cross-section is checked, and if everything checks out, then the application prints the final results, including the design strength of the cross-section. Now this is very similar to the Maple template that I showed you in session number 1. Here I am inserting the same parameters and clicking on Run in the Maple template to produce the results. You can see that the results are identical, but here we are plotting the cross-section and the ductility status of the figure. I will show you in subsequent sessions how to do the same, how to generate these plots using Python. This ends this session for today. Thank you very much for being with me, and I hope that I will see you in subsequent sessions. Best wishes.